So we are now finished with integration, and for today's lecture we'll proceed with estimating the derivative of a function. Okay, so for this lecture we will use the Taylor series. Okay, so I hope you are familiar with the Taylor series. So just a quick recap. The Taylor series is a useful function for uh, estimating, or you can replace certain function with the Taylor series. Okay, so say for example, you have this graph. Okay, or okay, say for example you have this graph and this is your x, and this point is x sub I with the value f of x sub I. And then what if you want to estimate the value of this point at xi plus 1? So you'd like to estimate the value around here. This one, f of xi plus 1. Okay, so this is your target value. And what if you don't know this graph, or you don't know the function? So you can use the Taylor series. So what is the Taylor series? So the Taylor series states that f of xi plus 1 is just equal to f of xi. Okay? So, anong ibig sabihin nito? Sabi dito, yung value nito is just equal to this one. No? So, based on this graph, parang hindi totoo. Or because there is a big difference. No? So, actually, this holds true if the difference between xi plus 1 and x sub I is very small. So, if say for example, if this is your xi and somewhere around here is your xi plus 1, so almost the same ang value ng f of xi and f of xi plus 1. So, it could be true. No? But based on this diagram, there's a big error. So, kung ganitong graph, pasabutan na niya. Pasabutan na niya is we are trying to estimate this function with this line. So, to make your approximation more accurate, so you need to add an additional term. So, what are the additional terms? Plus the first derivative of sub I times xi plus 1 minus x sub I. Okay? So, okay. So, what is this? This is a line. So, possibly, only siyang line. No? Kani? F of xi plus 1. By the way, we'll let this term to be equal to h. So, becomes h. And this one, the first line is okay, or the approximation, because that is an approximation. So what we observe is as we increase the terms around here, the error becomes smaller. So again, if we add additional terms, second derivative of h squared over 2 factorial. So this becomes a second order curve. So your approximation would be something like this. Okay, so this is f of xi plus 1 plus double prime. Okay, so again, if we add additional terms, so magkaduol na sa dire. Okay, magkaduol siya. So what we observe is that the Taylor series can actually estimate the function using this equation. Okay, so apa ni plus that because that is an infinite series. The more terms you add, the better is your estimation. Okay? Okay, by the way, the difference between this one is what we call h. So that is just a quick recap of the Taylor series. Now, using this concept, we will approximate the derivative of a function using Taylor series. Okay, so let's use what we call the forward difference. Okay, so what is this forward difference? Again, let's write the Taylor series. So the Taylor states that f of xi plus 1 is thus equal to f of xi plus first derivative of xi times h plus f double prime of xi h square over 2 factorial. Okay, so now our objective is to estimate the derivative of a function. Okay, so we will transpose all the terms to the left and we let this term remain on the right side. So if we rewrite, we have f of x sub I is equal to f of sub I plus 1 minus f of xi over h, then plus, or rather minus f double prime of xi, no, 2 factorial times h. Okay, So this is what we call the forward difference, because we are using, okay, so if this is your xi, we are using this value, the forward value, xi plus 1. Okay, so this will now be your, by the way, it is usually truncated here. Okay, so this is the first forward difference, or this is the approximation of the first derivative using the Taylor series. And as what you have observed, this one is what we call the truncation error, and all the terms. Truncation error. So using the truncation error, again, let's rewrite this one. And we let this whole term be equal to O. So you have O times H. Okay? Because divide naman natin eh. Kaya H square man ito divide H. So meaning you have, okay, so okay, so what you observe is that the truncation error is of the first order, meaning H. So take note that the more terms that you use for your approximation, the better will be your approximation. So since this is the first order, so the accuracy is not that good as compared to higher order. Say for example, H square. Okay, so we'll see that later on that if you increase the order of your truncation error, the better will be your approximation. But for now, we'll proceed with another method of approximating the derivative, and we'll use the backward difference. Backward divided difference. Okay. This one, forward divided difference. Okay. Or you can just actually say backward difference approximation. Okay? Backward difference approximation. So, unsa po ng backward? Reso na ako ni. Dali na lang siya. Backward difference approximation. Okay? So, kung na-forward, dapat backward. So, kung backward ka, you're using backward difference. This is your xi, and you will use the value before xi. So, muna siyang yun yung work back. Nasa back, no? Backward difference. Okay? So, unsa na siya? Meaning, kani mong estimate, no? F of xi minus 1 is equal to f of xi plus f prime of xi, again, final minus initial. Okay, hunong talian. Now, take note kani, kung butangan pa nato ni siya og value, say for example 1 and 2, ang atong 2 is xi, so meaning xi minus 1 will be 1 minus 2 or negative 1. So therefore, compare nimo sa xi plus 1. And take note nga, kani xi plus 1 minus x sub I is equal to h. Therefore, sample kani, kung 3. So kani, 3 minus 2, h equals 1. Ngayon, x sub I minus xi is 1 minus 2 is negative 1. Therefore, kani nga term di is just equal to negative h. So, mahitabuan ni f of xi minus f prime of xi h plus f double prime of xi x minus 1 squared over 2 factorial. Okay? So, sa may tabuan ni, this becomes f of xi minus 1 minus f prime of xi h. But since kani negative h, pero square man, so plus ar gyapon. F double prime of xi 2 factorial h square. And then next, basta add, negative na po na. So, alternating series na siya. Okay? And then, we transfer this one to the left side. You have f prime of xi. And then, f of xi minus f of xi minus 1 over h, and then get this one plus o for error, truncation error, times h. So this is what you call the backward difference approximation. Okay? And last is, you have also the central difference approximation or centered difference approximation. The third format of approximating the derivative is you have the center difference. So how do you get the center difference? So you write first the forward difference. Okay. Plus the second derivative. And then you subtract the backward difference. Okay? Oh no, let's write it first. Okay? And then you subtract this one. So this one will be cancelled out. This one also. So you are left with 2f prime of xi is equal to f of xi plus 1 minus f of xi minus 1 over and if we divide this one by 2h, okay, so what remains is the approximation for the first derivative using the centered difference. Okay, so to determine the error, again, this becomes if triple prime. This one is okay. So this is a third order divided by h. This becomes h squared. Okay, so meaning the error or truncation error for center difference is of second order. So what is the difference between second order and the first order? So say for example, if the error is just first order, if you decrease this one to 1/2 h, the error also is reduced by 1/2. Now this one, if you reduce h by 1/2 h, what happens? You have h squared over 4, meaning the error will be reduced by a factor of 4 or 1/4. Okay, so let's have an example and we'll use this function. And our objective is to estimate the first derivative of the function at x is equal to 0.5, 0.5, using estimate using forward, backward, and center difference. Okay, that is our example. Now our step size is using h is equal to 0.5. Okay, so first we will use the forward difference. Okay, according to the forward difference, f of x sub I is just f of x sub I plus 1 over h. Okay, so f of x sub I plus 1, so it is stated that you use your x value is 0.5. Okay, therefore, and your step size is by the way, this is your sub I, and then your step size is 0.5, so therefore this is 1.0. Okay, because difference between these two is your h. So you have f of xi plus 1, f of no, f of 1.0 is equal to, you substitute 1 here, and the result value for that is 0.2. Okay, 0.2. And f of x sub I, which is f of 0.5, is equal to 0.925. Okay, and also for since really getting the backward difference, your ano your x sub I minus 1 would be mga x sub I minus 1 would be 0. Okay, 0.5 to the left. Okay, so f of x sub I minus 1 is f of 0, which is 1.2. So with that, we are now ready to get the forward difference. So you have 0.2 minus 0.925 over 0.5. So the resulting value for that is negative 1.45. Okay, negative 1.45. Since this is a easy function or simple function, you can get the true value by evaluating the derivative of this one. The true value f of 0.5 or f prime 0.5 is equal to negative 0.9125. So compare natin na dire, we get the true error of 58.9%. Okay, that's a big error. Using the backward difference, okay, na lang ng backward difference. Okay, so this is the formula for the backward difference. Again, let's plug in these values. So you have 0.925 minus 1.2 over 0.5. So this will give you a value of negative 0.55. So again, the error for this one is 39.7%. Okay, last we will use the center difference. So for the center difference, okay, so this is the formula for the center difference. In the same way, let's plug in the values. So you have, you'll get a value of negative 1.0. So this will give you a true error of 9.6%. Okay, so you'll notice the gap between forward, backward, and center difference. So as you can see, the center difference gives a much better approximation in comparison between the two methods. That's because the center difference is of a second order accuracy. So that's one way of estimating the first derivative. Okay, you can use the center difference. Or there's another method wherein you increase the terms you use. Okay, for these three methods, we're just using up to first derivative. What if we increase the terms of the Taylor series and include the second order or third order? So that would give you a much better estimation. So uh, those are for estimating the first derivative. So how about the second derivative or the third order derivative? So for the second order, we're also going to estimate that one using the Taylor series. And this time we will use xi plus 2. Okay? Or we are using the step size of, if this is xi plus 1, this is xi plus 2. So we're estimating twice step size. So this is what we'll use to estimate the second order. So again, this is just equal to f prime of xi, and then xi plus 2 minus x sub I. And take note, based on our diagram, this is just equal to twice your h. Okay? So let's rewrite this one as 2h or 2h. Oh no. F prime xi 2h plus f double prime xi 2h square over 2 factorial. Okay, and then we'll use the forward difference. Forward difference is f of xi plus 1 is equal to f of x sub I plus f prime of x sub I h plus f double prime x sub I h square over 2 factorial. And then we will subtract this equation from this one, but this time we will multiply by 2. Nga multiply na 2 by 2? We'll say that later on so that we can eliminate this one. So this becomes minus 2 f of xi plus 1, and then this becomes equal to negative f of xi. Okay? And then this one will be eliminated. So plus this one is 2, and this one is 4. 4 minus 2 is 2, so you have f double prime of xi h square. Okay? Therefore, your second derivative, by the way, plus, oh no, later on. Okay, so your second derivative will be equal to f of xi plus 2 minus 2 plus 1 plus f of xi over h square. Divide na to. And then this one will be, what's the order? First order. Why? Because h cube man eh. Then divide na to h square. Munang first order. So this is the approximation of second order. And then in the same way, we'll arrive. By the way, this is the second forward finite divided difference task. I know. So we'll also, in the same way, we can derive the second backward difference approximation. No, second backward for the backward approximation for the second order. This is equal to, not to derive now. This is equal to f of xi minus 2 f of xi minus 1 plus f of xi minus 2 over h squared. So as you can see, we'll have 2h from the left. For centered version, okay, the centered version for second order, this is equal to f double prime f of xi plus 1 minus 2 f of xi plus f of xi minus 1 over h squared. And again, this is of second order accuracy. Okay, so let's continue. Now, there are actually two ways to increase the accuracy of your estimation of the derivative. First is to decrease the step size for the h. Okay, so based on the formula, for example, the forward difference, okay, so if you decrease this one, example 1/4, so again the error, you will also lessen the error. So that's the first method. Second way is to use higher accuracy or higher increase the number of terms in the Taylor series. Say for example, you use up to second order. Okay, use more terms in the Taylor series. And actually, there is a third way, and we'll discuss that later. Let's focus first on this one. So, how do we increase or how does it affect the accuracy? So, first, for a forward difference, it is equal to this equation plus f double prime Okay. So plus, so from the previous discussion, we have only used up to here and truncate this one as the error. But for now, we will use up to the second order. Okay? So our estimation of the first derivative would be equal to f of x plus 1 minus f of xi, and then this one minus f double prime of xi h square over 2 factorial, but since ano siya h dire, itong i-divide, may mo na dani over h kani may mong na plus o divide h, may mo na siyang second order. So na-increase karon ang accuracy sa imo ang first order or sa imong forward difference approximation by actually adding the second order na term. Okay? So, what is the value of this one? Second order. So, ang value ana niya is will plug in katong na-derive na to from our previous discussion. So, if you recall, ang value ani is okay, the value of the second derivative is this one. So, ito na plug in the ring. So, you have h minus f of xi plus 2 over h square plus f of xi, and then let's simplify this one, and you will arrive with this equation: negative f of xi plus 2 plus 4 f of xi plus 1 minus 3 f of xi over 2h. Okay? And then this is of the second order accuracy. So it is expected that this equation will give much better results compared to the previous approximation for the first derivative using only the first first two terms of the Taylor series. Okay, so for the complete list of derivatives, summation of the derivatives, just refer to these figures, figure 23.1 on our reference book. So you have here the first derivative, second, third, fourth derivative. So the first is the basic, okay, just the simple derivative wherein you just used or truncate up to the first derivative, whereas the second one is that you are now increasing the number of terms, so you employ up to second order term, so So this is what we have derived previously. So as you compare, the error now is of second order accuracy. For second derivative, this is the formula. So as what you have observed is that as you increase the derivative, the complexity is also increases. For the backward difference, these are the corresponding formulas, as well as for the centered difference. Now, if you have more time, you can actually derive this one by following what we have discussed previously. So just um, to give you just to give you an insight as to the comparison between the uh, accuracy of both formulas, can refer to this example. So this is the function that we have used previously, and the step size is 0.25. So the corresponding error is for forward is 26.5%, backward 21.7, and the center difference is 2.4. So mas accurate ang center difference. So what if we employ the first order approximation in these figures? So this one, actually we will use this equation. For the backward, we use this one, and for the central difference. Okay, so let's do that. So what you will need is these functions, or value of these functions. Okay, so I hope that you are now familiar on how to determine what is x sub I minus 2. So for this example, x sub I minus 2 is 0. Why? Because our x starts from 0.5, and then our step size is 0.25. So you go back 2 steps to the left. So that will be 0.25, and then from 0.25 to 0. So that is value of 0. So you will now get the f of 0, which is 1.2. And for the other x values, again, just follow the method. So for this example, the first order derivative, wherein our order of accuracy is second order, will arrive at a value of negative 0.859375. So the true error for that is 5.82%. So you can see the significant increase in the accuracy by employing the second order forward difference approximation. And for the backward difference, the error reduces to 3.77. And amazingly, for the center difference, the error is zero because nakuha niya ang true value, which is negative 0.9125. Okay, so as I have mentioned, there is a third way to increase the accuracy of the estimation of the derivative. So that method is what you call the Richardson Extrapolation. So the Richardson Extrapolation calculates two different values of step sizes, and then if you have the two values, plug in those values into this equation. So the derivative would be equal to the derivative of the second step size plus this equation. And usually, the ratio between h1 and h2 or is no, the ratio between h1 and h2 or okay, so by convention the ratio between these two, h2 is 1/2 of h1. So with that, h1 over h2 is equal to 2. Okay, so therefore, plug in this here, so ma-arrive ka nga equation. 4/3 derivative of h2 minus 1/3 derivative of h1. Okay, so this is now the Richardson extrapolation. So, unsa may kalindot ani nga equation? Magkuha ka og derivative aning h2 multiply by 4/3 minus 1/3 derivative of h1, you get the value of the derivative. So, dali ra kaayo siya. So, the question is, what is h2? So, ato na siyang may bawaan with this example, no? We'll illustrate that one using an example. Okay, so in order to get derivative of h2 and derivative of h1, so we will define first our step size. Okay, so our step size is h1 is equal to 0.5 and h2 is 0.25. Okay, because h1 over h2 is equal to 2. So, dapat i-satisfy niya siya condition para ma-apply tong d is 4/3 derivative of h2 minus 1/3 derivative of h1. Okay? So, para makuha na to ning derivative of h2 and derivative of h1, we will use centered difference approximation of itong first order accuracy. So, with that, f of xi plus 1 minus f of xi minus 1 over 2h. Okay? So, let's calculate first h1. So, ang pasabot aning derivative of h1, actually, this is just equal to f prime of lahi lang siya og notation. So, kung by the way, f of 0.5 gyapon natong kuhaon ani no, derivative at 0.5. So, kung mo na yung 0.5 and then our step size is 0.5, f of xi plus 1 is equal to f of 1. Tama? F of 1.0. Okay, 0.5 man ang atuang. Therefore, kung ang f of 1 ani is 0.2. Tama ba? based on our calculation, f of x plus 1 is 0.2. And then f of xi minus 1, ano man eh? Kung mo ni ang xi 1.0, xi plus 1, so ang xi minus 1 is ni 0. So f of 0 which is 1.2. Okay, therefore, mahimo na ni siya nga 0.2 minus 1.2 over 2 times h, 0.5. So you have 1, so this is negative 1.0. Okay? Again, ang error ani, calculate naman siguro natin na 9.6%. Derivative of h2, this is just equal to f prime of xi, but this time we will use 0.25 ang step size. So kung 0.25 na atong step size, may mo na ning 0.75. And then ang atong xi minus 1 is 0.25 xi 1. So you have f of xi plus 1, h equals 0.25 na niya. This is f of 0.75. Now, ang f of 0.75, the value of this one is 0.6363281. Okay? And then f of xi minus 1 is f of 0.25, which is equal to 1.1035156. Okay, so this becomes 0.63281 minus 1.1035156 divided by 2 times 0.25. So the answer for this one is negative 0.934375. Okay, so the error for this one is, again, makuha nimo ang relative error because makalculate nimo ang true value, which is negative 0.9125. Okay, so the true error is negative 2.4%. Okay, so using the Richardson extrapolation, saan naman din eh, this becomes, the derivative is just 4/3 times negative 0.934375 minus 1/3 of h1, negative 1.0. So the answer for this one is negative 0.9125. So ang error ani is 0%. Okay, so dali ra kayo gamito ng Richardson extrapolation. You just need to get two values for step sizes, two different step size, and then plug in the ending equation, you will get better value or estimation of the derivative. So that's all.